this method has really big benefits because this method overcomes the simplifications of strut and tie method. And you can see like the history workflow that the engineers are using a strut and tie as a standard analysis model, but we are coming with the different approach, which is called compatible stress field method and stress fields. Something to the theory, we are using a 2D plane stress task, so you can expect that you receive some 2 normal stresses and 1 shear stresses. This is representing on the element which is on the left side. And if you would like to, we are handling with the, or working with the principal stresses. So it means you need to somehow calculate the principal stresses. Everything is coming from the more circle. So if you rotate it, these elements, so you will find the angle where only principal stresses are developed, no shear stresses. But what I mean that what does it mean for our application? You know, I was meaning that it's a material nonlinear analysis. It means we are neglecting the concrete in the tension, and everything what is in the tension is covered by the reinforcement. So, and yeah, the tensile stresses are covered by the reinforcement, how I mentioned. So it's very important to say that. And this is the code compliant method. Something to concrete, how we handle with the concrete material properties, material diagrams. So the material diagrams are based on the Eurocode and the ACI standards. You can select or choose if you would like to design a structure based on the Eurocode like principle or ACI standards. So what is very important that we consider something what is called compression softening. So, you know, if the structure is like really stressed, so there are some transverse strains which are making the concrete softer, and you need to somehow capture this reality in the material diagrams or somehow. So we have it in the material diagrams. So we are using this green curve for capturing this effect, which is called compression softening. What about the reinforcement? Because the reinforcement is, you know, there is some mass of the concrete, so it's the rebar is embedded somehow in the concrete, and the concrete is coacting with the reinforcement. So in between the cracks, there is a portion of the tension which like helps to increase the stiffness of the rebars. Generally, it's a tension stiffening problem, or yeah, tension stiffening problem that like we are transferring this effect to the reinforcement rebars, that we are artificially adjusting the stiffness of the rebars based on the reinforcement ratio in the section. So this is the reason why we are using this blue curve that is unique for every reinforcement rebar. So it means we are reaching the same limit of the bearing capacity of the rebar, but you can see the ductility is different. So it brings you like lower deflections and more capture the reality. What about the model that is behind? Because I was mentioning we are using finite element approach. So we are considering a 2D concrete mesh that is, and the rebar that is the red one, the red curve, and you need to somehow connect it together. So we are using the bond elements. These are the purple elements that enable to transfer shear between the reinforcement and the rebars, and enable to slip the reinforcement. Oh, sorry, here is something that I should allow the recording or something like that. Sorry for interruption.
Yeah.
Yeah. Okay.
Hello. We record also the webinar.
Okay, perfect. Sorry for interruption, so we can continue. Yeah, and at the end of every rebars, you know, the rebars can have some different anchorage shape. There can be some hook, loop, and it's like it's mirrored to the spring that is at the end of the every rebar, and it's changing the anchorage length generally. Yeah, if you have some like a straight bar, so there is a different coefficient than for, let's say, for perfect bond or for hook or loop at the end of the rebars. Some summary about the theory that is behind, because it was only the taste of the theory. What we have more on our webpage, more deep theory, but I don't want to bother you a lot with this theory. So we consider it's very important to understand that we consider 2D plane stress. We are in compliance with the codes. All the material models are based on the codes, and we can check ultimate limit state and serviceability limit state also. So we can cover all all the importance of the codes and all the checks in the codes. What is very important that our software is verified and validated, because otherwise this is only the method which don't have any proof, but we have the proof that the method is working really well because we are closely cooperating with ETH University in Zurich, where like the head of the department is Professor Walter Kaufmann, and they are doing macro scale testing on the real like beams, real walls. So we have a force displacement curves and so many proofs that our software is calibrated really well. Right now it's time for the first workshop example. It's like this reverse T section. You can see on the right part of the screen where it's used, how can you use it, and I would like to show you how you can very quickly handle this problem in application detail. So let me just jump into to the application. Just the question: do the attendees have an option to like speak with me or?
Yes.
Yeah. So do you have some question before I start this example? If you have some question, please go ahead and ask.
Chat.
Yeah, and or you can use a chat, put the questions there, and we will answer it later. Okay. I will just open up the application. So I will just type in there IDEA StatiCa. Wow. Yeah. Yeah. Okay. Just open the project. Just give me a sec. Yeah, it's like this one. And I will start here from the scratch to show you that it's very easy to use. So you will jump in on the card concrete, and yeah, from the portfolio, the apps that can be used, we will be using a detail. Yet, I think, is there some question? No, it's okay.
Does the method check notes? In the chat, we have a question.
Mm-hmm. Okay. Teach it. Yeah. And does the method check notes like a yeah, there is a question from the audience. Hi, does the method check nodes like strat and tie strat and tie methods supposed to? No, there is a different approach. It's based on the principal stresses. So it's not like the same approach based on the strat and ties like strat and tie method. It's completely like a different approach. We are checking the whole structure, the whole continuum of the structure, not only the like the nodes and the struts and the ties. We are checking the whole model that you will see. Yeah, so I think it will be evidently seen on the first example, and yeah, it's covered the code EC2. Yeah, there is another question if we covered the Eurocode 2. Yes, we are covering this code. We covered this code. Okay, fine. Okay. So I will just jump into the application. If here are some users of the application IDEA StatiCa connection, so you can see that the layout of the first page or first view is the same. So we have split it, the application into the 4 peers, where you can select the model type, class, topology, and put there some parameters. So from the model type, you can select only 2D, but in the version 24, there will be something else. And from the point of view of the class, so you can select from some predefined topologies, and that will enable you to make it quicker, your design. But we'll start from the scratch because I would like to show you how powerful it can be and how very easily you can use it for design of the reverse T-beams. So I will select the concrete grade from the library. It's very easy to use C35/45, reinforcement B500B, and you can see that we can also use the pre-stressing, but for this example, it's not relevant. The general concrete cover is, we can stay by the 30 millimeters. So let's create the example. Yeah, and right now we are in the application. So you can see we split the application. There are some cards. There is a ribbon that for every cards there is a different settings and different options which can be turned on and used. On the main application or the main window is the like a window for modeling part. And on the right side there is a property grid, we call property grid, where you can input all the parameters for changing the geometry, putting the loads and the stuff around. So I will create a new model entity, and I will start with the general wall. So there will create some element where you need to set up only the width and the height. So the width is like 80 millimeters. So I can put here 0.8. The height is a 0.3, and the thickness is 1 meter. Because I would like to cut out the 1 meter segment from the beam. And if I show you how it looks in the 3D, so this is our 3D rendering with all the coordinates and all the dimensions. So it's very easily to render and read out all the parameters and all the dimensions. So I will stay by the 2D mode and create another wall. Right now I will create another wall that will be connected, tied up with the first one. So you can see this is my first wall. I will just copy the operation and change the width and the height of the wall because I would like to create this T section. So 0.4 is my width, 0.8 is my height, and yeah, we need to right now use the like a positioning. We need to somehow put and create the geometry based on the master and the insert point. So I will select the first wall. This is my reference wall, and you can see on the elements being displayed the nodes. So it's very easily to fit and join together 2 nodes to create geometry you want. So my master point is on the first element. It's master point 7 and insert point 5. So right now, if you check the geometry, so I have created some cutout from the beam structure to assemble and code check the discontinuity regions that looks like this. Right now, what about the boundary condition? Because you can see the structure or the software informing you that the structure is statically overdeterminate, so you need to put the boundary conditions for like analysis, because without boundary conditions, it's like moving like a rigid body and you don't get any results. So how to do that? From the point of view of the supports or boundary conditions, we have a portfolio of the 5 supports that can be used, and every support is suitable for different type of the structures. For this, let's say, indirectly supported beams or reverse T-beams, we are using this patch support that are in placed in the structure, and in some radius you are like catching the rebars, and you will tie up this support with the rebars, so you will represent the model you want. Right now, from the point of view of the boundary conditions, so we have a 2 degrees of freedom in the X and the Z directions, which can be used for this type of the supports, and we need to place it somewhere. I would like to place it here at the top of the beam, because here it will be hanged, and all the forces will go through the supports to the rebars. Yeah, and we will tie it up in the reinforcement, the support with with the reinforcement there in this reinforcement option. Okay, so let's place it there. The effective radius is like a 50 millimeters. Sorry, 0.05. The radius, it's up to engineer. It's engineering judgment what radius you will use for that, how many reinforcement will be catched. And we will be using the master element will be wall 2, and I will use the points to coordinate my my support. So the master point, I will start by my master point 4, and the X and the Z position will be 50 millimeters on the right and 50 millimeters to the bottom. So I have placed the support very, very quickly. What I can do, I have the option to copy in the same way the patch load 2 and place it to the point number 3. So I will use the point number 3 and just switch the sign in the minus and reverse it on the other side. So right now, the best way is to have like a simply supported structures, because if it's over constrained, yeah, there can happen some effects which you don't want. So I will release it in the X direction, so there will be no other secondary forces that will appear there. So you can see the software is warning you that there is no reinforcement reference to the patch load. Yes, but because we didn't put it there, and we will put it later. But at first, let me put there some bearing plates, because at this part, I would like to put there some concentrated forces. And, you know, it's a 2D plane stress model. There are walls. So if you would like to use a point load, so you need to somehow redistribute it to the structure. Otherwise, there will be some singularities on the structure, and the structure will be locally damaged. So this is what you don't want. So I will use the model entity, and the last part, it's like a load transfer devices. These are devices that can be used for transferring of the concentrated force. So I will be using these bearing plates. It's like the bearing plates will be like really on this place. So I will put there only the dimensions. So the width is 150 millimeters. The thickness is very important parameter, because, you know, if it will be really slender, so there will be some local peak here. And if it's very thick, so the redistribution of the force will be uniform. This is generally what I want. So you will use this thickness based on the real parameter of the plate that is there. Yeah. So it's my location. I will just copy the operation and put it on the other side. So you will just very easily switch it from the measurement, not from the beginning, but from the end, and you have placed the support immediately. So this is my model, how it looks from the point of view of the geometry and the constraints. I have finished, and right now is the time for putting the loads. I was mentioning that we are using the material nonlinear analysis inside, so we are handling with loads, external loads, not with the internal forces. Yeah, so there is a combination of the loads. So you will move on to the load cases, and in the load cases you need to select if it will be permanent variable or pre-stressing part. So it's very important for the code check. Yeah, okay. Fine. So the first load case is permanent, and the force will have a magnitude 150 kilonewton in the Z direction. So this is my global X and global Z direction. So I will use the plus button, and from the loads that can be used, I will use a point load. The point load, you can see he automatically check if there is some bearing plate and put there the forces. So if I like extend the window, so there is a magnitude is minus 150 kilonewton, and it's placed in the global Z direction, and the transmitting devices is used as the bearing plate 1. If you switch it to bearing plate 2, it's automatically switched there. And you can also use some inclination if you want, or some eccentricity, so you can like move your force wherever you want. Right now, I will just make it simple, put there 150 kilonewton, and copy my force to bearing plate 2. I have created the first load case, and right now is the time for preparing the variable loads. Yeah, because later on these are first one load cases, later on combinations. So I will just copy or create a new one. I will just copy this operation and switch from the permanent to variable. The intensity of the force will be lower, so there will be only 100 kilonewton, and that's it. So I have prepared 2 load cases with different load case type, and I will be preparing 3 combinations. The first combination, I will create the 3 of them. The first combination is for ultimate limit state. Second combination is for serviceability limit state, which will be characteristic for stress limitation and crack width. And the last one is quasi-permanent. So we just switch it and you have the prescription. What we don't have right now are the partial factors. And the partial factors has to be put it inside. So you will go through the pen and just very easily put there 1.35 for permanent, 1.5 for variable, and for characteristic and variable loads, or sorry, for characteristic combinations, we will use the partial factor 1 for permanent load and 1 for variable load. Yeah.
We have some questions.
Perfect.
Can
Yeah.
you check one
Yes.
simple and one maybe?
Okay, so I will. Sorry, is the method of calculation accepted by Eurocode 2? It's based on this Eurocode provision. So yes, it's accepted by the committee because there are the same assumptions and same material models. So yes, it's accepted. Yeah. Can you please clarify the support conditions? Why are the supports at the top? Or those the lifting elements, or how it's being actually supported? Yeah, maybe I didn't mention what I mean from the point of view of the modeling. So I will just make a screenshot and show you what I'm thinking. So in my model, I consider just simply supported beam like that. So this is my beam that is like laying here on the wall, and I'm cutting, let's say this part, and I would like to do the design and the code check of this reverse T-beam or this part, because, you know, it's a discontinuity region, and I would like to know how many reinforcements I need to use to cover, let's say, the cracks which will appear here, and what can be the maximal force, or if I'm able to transfer this force via this model. So, and this is the reason why I use the supports also here, yeah, because these supports will not affect the behavior of the structure itself, because my area of the interest is here from the point of view of the concrete in compression, and from the point of view of the tension, I know that the maximum force will be here. This is like, it's like the engineering judgment, you know? So the supports will be placed here. Otherwise, maybe you have another experience where to put the supports, or how to handle a structure like this, but generally this model is also supported if you check to our committee. So there are the examples for design and the code check the structure like this, and how the stress is redistributed to the reinforcement rebars and to the concrete. So based on these assumptions, we used the support at this location. Okay. Yeah. Just check the question. I'm very happy that you are putting the questions. How is the type of the cement taken into account when characterizing concrete from the point of view of the durability? Can you use any type of cement to produce pre-stressed concrete, the soft imposed or restrictions? Yeah. So generally, from the point of view of the material properties, if you go in here, so these are the parameters that are like coming to the calculation from the point of view of the concrete. Yeah, and so we have from the point of view of the physical properties in some mass for us, and from the point of view of the Eurocode 1992, what we need for the calculations is exactly here. We need the strength, we need the models of the elasticity, we need some the tension strength of the concrete, and also we are selecting what diagram type will be used. Yeah, so other properties are not important for the material nonlinear calculation, and you know, we have a library of the material properties which is based on the Eurocode. So from the point of view of the concrete that can be used and select, you can see it here. We have a concrete C12/15 till C90/105, but you can create your own user-defined material with your user-defined properties. Yeah, so you will just jump into material properties. You will just copy this property of the concrete. You will change it. You can put there what strength you want, but it's very important that these parameters are going in to the calculation of the stiffness matrix, and also are like responsible for the outputs. Yeah. So this is, I hope I answered your question. Maybe what you're mentioning here, the next example that will be covering the pre-stressing, this answer will be like answered there, and will be more clear for you. Okay. I hope I answered the question. And let me move on to combination rule and continue. And for the quasi permanent combination, there is a permanent load case that I will keep it as a 1. And for variable, I can use like a 0.6, because the variable load case can be like a snow, and can be, you know, it's based on whatever type of the loads you expect like the variable. So I consider the factor 0.6 just for demonstration. Right now, what about the rebar assembly? Because I was mentioning that the concrete is covering everything what is under compression, and what is in the tension is covered by the reinforcement. So if you run the analysis immediately, so the model will explode because there is no reinforcement, and this is a no strength. So what about the reinforcement? I will show you how very quickly you can design or put there the reinforcement. So we have some tools, some predefined reinforcement types that can be used. And I will select the group of the bars. From the point of view of the group of the bars, I will just show it in the 2D rendering. And I will create a loop or the stirrup that will be like consecutively going over the edges. So, but it's better to show it in the 3D because it's better for your visualization. So number of layers. So there will be only one layer, and the diameter will be 14. There is a 6 bars in a layer, so it means I have extended the number of the layers, and I would like to put it on the more edges. Right now you can see it's like it's aligned only with the bottom edge. So I have the option to define the the bar not only on the outline or opening edge, but I can use it on more edges. If you hit this button on more edges, and you will select the master element. This is the wall 1. This is the wall 2. If you turn it on, I can see it. It's wall 1, wall 2. And I will switch it into the 2D. So you can see the number 1, 2, 3, 4. So I will just put the numbers here, 1, 2, 3, 4. And I have created the enclosed stirrup. And at the end, I will use this standard hook. So it means I have created some spring at the end of the at the end of the rebars that will cover the anchorage length and reduce it. So this is my geometry of the reinforcement that is in the flange of the T-beam. And right now I will use the same approach for a web. So what you can do very easily is to copy this operation. There will be the same amount of the rebars. I will also use it on the more edges, and the outline or the master point won't be wall number 1 or wall number 2, but I would like to use both because there will be some penetration of the stirrups across the high of the beam. So it will be some reinforcement inside the wall 2 and also inside the wall 1 to bind it together, to tie it up. So from the point of view of the edges, so I will use 8, 3, 6, and 7, and I will create the stirrups like this. Yeah, so it's very easy to use because we are using the numbering of the edges. So if I check it in the 3D rendering, you can see I have created the model. There is no longitudinal reinforcement because we are handling with the 2D plane stress model. So this direction is generally not like a real. There is the thickness is like a parameter of the thickness of the stiffness. Sorry. So this is the model what we are using, and right now, what I need to do, I need to interconnect this support with the reinforcement. Here in the bottom, there is an interconnect automatically. If you will do it, I will create some radius, and in this radius, there are some constraints that will catch the reinforcement rebar, and it's like it's holding there. Yeah, so there is a constraint that is holding the rebars, and all the forces are going through that. Yeah. So what now? Right now we can jump into the tool. Let's imagine that this example is like a straightforward from the point of view of the reinforcement, because you have a beam, you know how to reinforcement, and you will use the same reinforcement as you have for a beam analysis and check if it's sufficient or not. But let's imagine that you have some detail where you don't know how to reinforce it. So we have a tool that will help you to recognize where to put the reinforcement. The first one is a linear analysis. It's very handy analysis. You can use it in every software like ETABS, SAP 2000, Midas, whatever, wherever, and you can check it in the vector view. So here is a big portion of the tension. So I can expect that here will be like a big crack, and I know that I need to like put more reinforcement to cover the cracks. So this is my first idea or first tool that will help me to identify how the structure will behave from the point of view of the linear way. This is the linear analysis. This reinforcement is for the analysis neglected. It's very important. The second option is the topology optimization. Generally, topology optimization gives you the results based on the most stiff shape of the structure. So it means I can select from the percentage of the volume. So if I check the 2D, the 40% of the volume, so I can get something what you know from the literatures, from the codes. So these are some compression struts, and these are some tensile areas. It's very important to say that it's a linear topology optimization. So we consider some linear properties, not changing of the stiffnesses and so on. So this is like tool that will help you to identify where are the tensile areas and where are the compression areas. The white areas, these are areas which are not, let's say, not used, are not these are the areas where generally the energy is very low. So yeah, so this is the reason why this analysis will help me to identify where is the best way where to put the reinforcement to be utilized across the section. So this is what I have here, and I can go into the check. The calculation is very swift. So you will run it at first is going to the solver, the C1, later on C2, and later on C3 combinations. So what you can see, the first insight to the results. On the left part, there are some ultimate limit state combinations and code check of the entities, like a concrete reinforcement and the anchorage, with all the critical values that are displayed in the locations where it's critical. From the point of view of the serviceability limit state, like the crack width, stress limitations, and also the deflections, I can see that I'm perfectly on the good track. Everything is like shining with the green ticks, and I would like to know more. I would like to know more what is happening, because it's not enough for engineer that see that there are some percentage of the utilization, but you would like to know more how the structure behaves, what is behind. So here you can display the reactions. You can see the reactions has to be under equilibrium. So there is a 110 kilonewton and 110 kilonewton on the left side, also on the right side. So on the right side, you can see that there is a check of the equilibrium. So all 100% of the loads has been transferred and is carry over the structure. What about the strength check? So right now I'm in the part of the ultimate limit state, and my area of the interest is here. This is my area of the interest. So I would like to check the concrete strength. So the critical place is here. It's minus 4.3 megapascal. So you can see the utilization of the concrete is very low. So it's only 26% from the capacity. So this is my, if I turn off the reinforcement and turn on the mesh, you can see how it's meshed. We are preparing the mesh for you, and the area where are some transmitting devices or some it's locally like refined, because you need to refine the area where is some local concentration. So this is how it looks from the point of view of the concrete. If you would like to play around with the mesh, of course you can't. You will go to the settings and play around with the mesh size. What about the reinforcement? From the point of view of reinforcement, I would like to see what is happening on the structure. So you can see the stirrups that are like maximally utilized are the stirrups in the wall number 2 in this web, because this is there is a big portion of the tension. Also, the horizontal rebars are utilized a lot. So this is how the structure is covering the tensile stresses.
You have a question?
Yeah. Are the loads applied per meter of element, or do we consider the span when we add them? How does the span of the beam influence the input? It's 5 meter span or 7 meter span beam, for example, for dimension to dimension it correctly. Yes, so there are like a multiple questions in one question. So I will answer. Generally, how I draw here, there is you can expect that this has a 7 meter, but generally it doesn't matter right now, because if you would like to do the coating of the beam in this direction, so you will use some beam analogy and use put there some stirrups, put there some longitudinal reinforcement and do the code check. For us, where is the area of the interest is that it can be close to the support, it can be in the middle of the beam. So it's up to you right now to investigate the beam. But let's say if I take the beam into account, so I have considering, let's say, this scheme, and the loads will looks like this. So I consider that here, if you take out the 1 meter, so and the loads is uniform, so you have some force that is, it's a uniform load, and you will cut out 1 meter. So I have considered 200, I think 250 kilonewton force, but there is 1 meter, so it's like a 150 kilonewton per meter. It's the same, yeah. But you can of course cut out like only the 40 centimeters, let's say, but you need to take into account also the loads. Yeah, so you know the loads from your FEA, from your global model, and based on the thickness you put to finite element method to detail here, you need to also handle the loads. Yeah, so I consider 1 meter, so my uniform load is equal to the force. Yeah, sure.
Why is anchorage?
Yeah, why is the anchorage in most models 90? That's very good question. That's very good question, but we need to, sorry, I will just turn off my quit it. Okay. I need to draw the material diagram for the anchoring to explain it to you why we have it like this. So this anchorage check, at first you need to understand what material diagram is used, because there is some bond model. So if I draw the material model, and here is a tau b, it's like a design bond stress or bond stress, and here is a delta, so it's a slip. Yeah, it's a slip between the reinforcement and between the concrete. So in a real way, from the real experiments, it looks like this. Yeah. So you have the first, like the initial stiffness, it's very stiff. And if you catch the peak, so it's going to the post-critical behavior, and later on it's only on the plastic branch, and there is only this like only the slipping without increasing the force. What we consider in IDEA StatiCa to capture, let's say, because right now we have a ribbed bars, but let's imagine that you would like to use, let's say, a different type of the bars that will be, let's say, without the ribs. So this level will starting to be different. And we are not capturing the reality because we are a design software, yeah, and we are using a design material properties that are coming from the Eurocode. So we are using what is written in the code, and in the code is something like this. We call it perfectly rigidly plastic diagram, that here is a tau B, tau BD, yeah, it's a design bond stress. And this part is like fully plastic with only small inclination in this plastic branch. So it means in very small slip, if you have very small slip between the reinforcement and between the concrete, so you are immediately on the 99% of the utilization, but we have very long branch. So this 99% can cover, let's say, twice time the load, because, you know, there is a big plasticity. If you would like to know more, so please go on our webpage. I can show you here. If you go on our webpage, here is the support and learning. Here is the, here is the support center. Here is the theoretical background. And here is the theoretical background for IDEA StatiCa Detail. And if you go in, so there is a part which is dedicating to anchorage, and there is explained this diagram in detail. Yeah? And there is also written why in almost all cases is the utilization in between 98 till 100%. Sometimes the utilization is also over. There is, let's say, 102% and still satisfying results. All these like aspects of the calculations are explained here in detail in theoretical background. Yeah. So I hope I answered, because we should talk about it like hours, but yeah. And there is very long questions. I can just put it here to everybody can read, right? According to Eurocode 1992.1.1, indirect supports the shear reinforcement in the beam that you calculate in this example must be added to the direct shear reinforcement. Shear caused by the girder self-weight and other loads that are acting on the top of the beam. Can you account for this in a single model in IDEA StatiCa, or you have to perform I have to perform two models. Yeah, it's very simple to say. I have to perform two models. The first one in reinforced complete section, yes. Second one, yes. I think you answered your questions. So you need to use the two models.
La ultimul, la ăla nu.
Okay, so generally in order to finish this part of the check in the time around 10:30, please send us the rest of the questions
Parcă era mai lat.
info at reflexsoftware.eu. Yeah, thank you so much. I'm very happy that you are sending, you are interested in about the software. You are sending so many questions. We will answer. Zole is sitting next to me, so he will answer all your questions very swiftly. Okay, so I will go to the next point. Is the anchorage. Right now we are hitting the point about the anchorage. You know, this check will cover that your reinforcement won't be pulled out from the concrete. Very important check. And what you can expect in IDEA StatiCa that will gives you from the point of view of the check. We will give you the bond stress that is on the rebar. So, you know, you can if you jump into the code, there is a chapter that is dedicated to anchoring, and you can calculate based on the concrete grade your design strength or tau BD. Yeah, so very easily you can calculate it. Our tau BD here is the stress. You can count it from the utilization, but it's very important to say that we are displaying the bond stress. The marginal bond stress is at the beginning or at the end of the rebars, because you need to somehow fully anchor the rebars, and if it's fully anchored, it can transfer the loads to the other parts of the reinforcement. So you can display the force on the rebar. Yeah, so you don't need to calculate it by hand, so you will just hit on this button and you can immediately see that the force at the rebars is 246 kilonewton. Yeah. So this is, and I would like to see the bond stress divided, or the stress divided by the bond stress, and I can see immediately the maximal spot with the utilization. Generally, if you would like to know more, you can just hit the right button and I can show the chart. So this is the dependency between the force, or sorry, between the utilization, and on the horizontal axis, there are the increments from the permanent and from the variable loads. So if I check, so for increment of the variable or for permanent load, there the reinforcement being utilized only for 82%. But if I put there another load, like the variable, the utilization has been increased about approximately 18%, and I reached the target 99.8%. Yeah, so you can very nicely see it on the graph. If you hit the right button, you can also export it to the CSV, DXF, or a bitmap. So this is the really good benefit to gives you the insight, or like a deeper insight to the problematic. Right now, it's been checked for ultimate limit state, but what about the service celebrate limit state? Stress limitation. What you can expect from the stress limitation. So this is the code check that is covering two conditions. The first condition is for concrete, where we consider the limit. You can see the limit of the stresses is 15.8. What does it mean? If you check this clause, the 7.2 in the parenthesis 3, so there is written that you need to ensure for linear creep the limit 45% of the FCK. If it's higher, the code check is not satisfying. And there is also the check. For characteristic combination for 60% of the loads, or sorry, the 50% or 60% of the strength of the concrete. And if it's exceeded, so the results are not passing. And you can see that we also consider some short-term and the long-term behavior of the structure. What does it mean? That for the code check of the service celebrate limit state, we are considering some effective models of the elasticity, and we considering some creep. Yeah, it's very important for code check, because the structure, or like the concrete structures, the composites, you need to check it in the 28th day, if we are talking about the concrete, like the reinforced structures, and let's say in the 50 years. And how you will cover it? You will cover it by the effective modulus of the elasticity by the creep. The creep factor is by default 2.5, but you can customize it. You can calculate it somewhere and put your precise value here. So you will just edit the parameters, change it, save it, and use it for your calculation. So I will move on to the check again. And what will happen if I switch from the short term to the long term? You can see for a short term, the value is 3.4 megapascal. But if I hit the long term, you can see it's being changed from 3.4 to 3.3. The same for reinforcement. There is the condition where you need to cover 80% of the characteristic yield of the rebar, and we have a rebar B500B, so it's 400 megapascal. You can see, so we are reaching the limit 71%. What about the crack width? This is very important check for reinforced concrete structures. The limit is changing based on the exposure classes. By default, there is a 0.3 millimeters. And you can see, because we are using the model, it's a crack smeared approach. There is no discrete cracks. So this is the reason why everything is based on the material diagrams. And you can see the maximal crack width, but also what is very important, the direction of the crack. Yeah, so this is my direction, and you can see that the crack will be perpendicular to this direction of the cracks. So it's very nicely seen how the structure or the detail behaves and what are the mechanism of the failure. Yeah. What about the deflections? I think is the most important check at first to see the deformed shape. If you check the deformed shape, so you can see how the structure is deformed, and it will gives you the clue that it's correct. It's correct. Of course, these boundary conditions somehow affect the structure a little bit, but you need to know what is your like area of the interest. For my area is the interest is this part. Yeah, so this is the reason why the results here won't be somehow a little bit affected by the constraint, but it's everywhere. It's in every finite element solution. Yeah, so it behaves really good. And I can also display the short-term deflection, long-term deflection, some increment of the variable loads, or sum of all deflections together. That gives you the maximal deflections is 1.2 millimeters. Yeah, and there is the last one, it's auxiliary check. This is, let's say, for advanced users, if you would like to display the tensor of the stresses, the directions after the cracks, after the nonlinear analysis. So you can very easily read out the angle that is happening on the structure. What about the report? Every static calculation or every numerical solution should have a really nice report, because report is very important for like the summary of all your steps. You can see we have really nice report that you can just drag and drop and switch in between the chapters, and you can customize your project. What you can see a geometry, you can see some boundary conditions, you can see some combinations, and of course results. All the results that we went through and many more are displayed very nicely in this graph. You can export it to the Word or PDF, and you can also turn on the bill of the material. It's very important for the engineers to know how many reinforcement is there, and also what are the dimensions of the and what are the lengths of the rebars, what is the mass, what is the volume of the concrete that is inside. So you have it here in the step. There is some overview of the weights and so many more. But what is more important, that you can export it to the DXF, and if you export it to DXF, so you will get the drawings. You will get the drawings that is in the DXF, and it's in the block, everything, you will explode it and use it. Everything is described there. Sorry, I don't have a VPN, so I cannot show you how it works, but you will just hit the DXF button, export it, and that's it. So I think it's all from my side for this first example.
There's a question. Do we have time to
Yeah, if we have a time, we can answer the question. Zoli, what do you think? So we can answer, right?
Or maybe you can present the 3D concrete.
It's like I would like to have it at the end of the presentation.
Okay.
Yeah. So okay, I can. Yeah, I will answer the questions. I will just show it here. Fine. Is there a sound issue? Oh, okay. I hope everything is fixed right now. Everybody can hear. Okay.
Maybe you have time for one more question.
Yeah. Okay. I see there is a possibility to introduce low concrete strength class like C12/15, C16/20. Such compressive strength classes are not possible to be used in a usual concrete application, normal or pre-stressed, due to durability restrictions in Romania. Can you introduce somewhere the exposure classes X from durability point of view in order to obtain the minimal concrete strength class? Generally, this software is general and is based on the general Eurocode. We do not have any national annexes there to generally restrict the other people of usage. Yeah, so it's like we are code dependent, but from the point of view of the national annexes, we do not support. We don't support the national annexes to have the variability of the usage of the software. So if you would like to change something there from the point of view of the material properties, and let's say it's restricted in the Romania and you cannot use it, so you can create your own library of the material properties, but the general exposure classes, you don't have an option to select any exposure class.
One more last question.
Yeah, in some situation, I want to ignore anchorage. How can I do this? Okay, maybe it's funny, but you can somehow delete it in the painting from the report, but otherwise we do not have an option to turn it off. I will just give me a sec. I will just check, but I don't think so. Yeah. The anchorage check has to be in all time considered, so you cannot turn it off. It's not no other option to turn it off. Yeah, the question is why. That's very good question. I have to admit that I don't know why, because we would like to be code compliant, so you cannot just very easily turn it off. I think on these questions I cannot answer. I need to ask the guys why there is no option to turn it off. Maybe it will be dangerous for the users if you turn it off, so there will happen something. And for the unexperienced users, it can be very dangerous, let's say. So, but yeah, it makes sense if you are a very skillful engineer and you know what you are doing. You can have an option to turn it off. So we can discuss it with our guys to have the option to put it to our settings, turn it off the anchorage. Why not? Yeah. But I think here is also with me the Thomas that is responsible for or is in the part or in the team of the developers. So maybe he has more information than me, and he can send you the message here if there is some option or some future request will be accepted by the developers. Okay, I think that's it from the point of view of the first introduction of the software. And let's say we can get like a 5-minute breaks.
Sure.
Yeah, and we will continue with this pre-stress beam.
Mulțumim pentru prezență. Dorim să facem o pauză scurtă și revenim. În continuare așteptăm întrebări pe adresa afișată pe ecran. Sper că se vede și ne vedem peste 10 minute. Vă mulțumim!